Hello everyone, my name is Dario Chisholm, and today we will talk about non-local information encoding and the emergence of quantum Darwinism. Our goal for this talk is to try to understand what are the effects and the consequences for quantum Darwinism and thus for the emergence of objectivity when the information about the system is encoded non-locally into the environment. The co-workers for this work are Luca Innocenti and G. Massimo Palma, and this work was done, we're all working at the University of Palermo. So first, let's make a very brief review on what is quantum objectivity. In the quantum realm, we define objectivity as consensus between observers. The idea is that when we have a system, the system interacts, of course, with an environment, and the environment is made by some constituents. Because of this interaction with the environment, the system will go through decoherence, and after the interaction with the environment, we can have a bunch of different observers, and each observer can have access to one environmental fraction, and the observers will be able to infer information about the system by making measurements on their environmental fraction. If they agree on some property that the system may have, then they reach a consensus, and if there is a consensus or some property of the system, we can say that the property is objective. And in quantum Darwinism, we quantify objectivity by using the quantum mutual information between the system and an environmental fraction. That is, the entropy of the system plus the entropy of the environmental fraction minus the entropy of the joint system environmental fraction. And we do this as a function of how big the environmental fraction actually is. And if we have an objective state, the plot of the mutual information as a function of the environmental fraction size will be something that looks like this. So it will reach a value of 1 for very small values of the environmental size, and it will reach a plateau so that it won't increase even though we keep increasing the environmental fraction. And this means that we can define a quantity f of 0 such that the mutual information, it's the minimum quantity such that we have a good amount of mutual information between system and environment. And then we can define redundancy as 1 over f of 0. The idea is that if with only f of 0 fraction of the environment I can already infer good information about the system, then I can cut the environment into roughly r copies and give each fragment to an observer, and the observers can make their measurements and reach consensus. Another framework that deals with objectivity is spectrum broadcast structure that shares the same core ideas of quantum Darwinism, but it's more of a geometric approach rather than entropic. The idea of spectrum broadcast structure is that the state of the system is objective if it has the following general form, where we have a sum over all the possible state of the system in tensor product with certain state environmental states. And the key requirement here is that the different environmental states corresponding to the different states of the system are perfectly distinguishable from one another, which means that the observers will be able to use these environmental fractions in order to infer information about the system. And in SBS, redundancy is nothing else than m, which is exactly the number of environmental fractions that in which I'm able to partition the environment, such that the global state has an SBS form, which then again is how many fractions I can give to the different possible observers. And there's also a hierarchy between SBS and quantum Darwinism. SBS is considered to be more stringent than quantum Darwinism, and as a matter of fact, If we know that a system has an SBS structure, then we know for sure that it also satisfies objectivity according to quantum Darwinism, but the inverse is not necessarily true. When we know that a system is objective according to quantum Darwinism, there are some extra requirements that we need to meet in order to be certain that the resulting system is SBS. In our work, we want to study what are the effects of non-local information encoding into the emergence of quantum Darwinism. But first, let's try to understand what we mean by non-local information encoding. So let's assume for now that our system is a qubit, and we want to encode information about the system into an environmental fraction. And in this example, our environmental fraction is made by 4 different environmental constituents. And the information is encoded in such a way that if we make a global measurement on the 4 qubits all together, then we can actually understand, for example, whether the system is in the 0 or in the 1 state. However, if we miss even one of the environmental constituents, then we will lose all of our ability to infer information about the system. So non-local really means that the single individual qubit holds no information at all. It's only all of them together that allows a potential observer to recover relevant information. So these are what we want. We want our information to be non-locally encoded, and now we need to search for the states that will allow us to do so. Since we decided that our system is a qubit, we only need 2 states to encode information about the system, and for now we decided to call them plus tilde and minus tilde. An observer needs to be able to read these states and extract information about the system, so a fundamental requirement is that these 2 states are orthogonal to one another. That means they're distinguishable from one another. And non-locality means that when we lose even 1 qubit, then these 2 states are not distinguishable anymore, which means that they will be identical from one another. So when we do a partial trace over plus tilde and over minus tilde, the 2 resulting states will be identical to one another. And it's very easy to check that states that have all of the requirements that we need are the following. Okay, so the minus tilde and the plus tilde states, that we could say they are some sort of generalized G8Z states. And the global state, the system plus environment, will have this form. So we have the environmental fractions in the plus tilde state if the system is in the 0 state, and the environmental fraction in the minus tilde state if the system is in the 0 state. And as you can see, this global system and environment state has an SBS structure. And for reference, this is a reminder of what is the SBS structure in general. So once again, we have a system and we have some environmental fragments, and each environmental fragment holds all of the relevant information about the system. However, this is true only because each environmental fragment is actually made up by a bunch of other environmental constituents. And the information into these environmental constituents is encoded non-locally. As a counterexample, here we have instead a case in which information is locally encoded. Now, observers in general do not have any information about the structure of the state. Thus, when they decide to make a measurement on the environmental fractions in order to recover information about the system, they really need to pick their environmental fractions randomly. Okay, they cannot really choose. They can choose, but they have no way of knowing which would be the better choice. But if in the local scenario it really doesn't matter which environmental constituents the observer is measuring, because he will be, on average, be able to recover relevant information about the system. In the non-local case, it may very well be that none of the chosen qubits hold relevant information about the system. So the observer will remain ignorant about the state of the system. So when we decide to compute the quantum-mutual information in the non-local case, we also need to take account about the probability for the observers to pick up, let's say, the right qubits, the right elements that will hold information about the system. And this is what happens when we compute the quantum mutual information between system and environmental fraction as a function of the size of the environmental fraction. Here we have chosen a degree of non-locality that is 4, and as you can see, for example, for a value of redundancy of 40, we have no plateau. So it means that even though there are 40 copies of information about the system into the environment, because of the non-local way this information is encoded, and observers will not be able to reach a consensus. They will not, on average, be able to recover information about the system and agree with one another. At the same time, we can see that as the redundancy value increases, we slowly reach a plateau. So a large value of redundancy can compensate for the effects of non-locality. Non-locality will hinder objectivity, but of course, high redundancy will compensate this effect. So far, we have focused on a very specific way to encode the information, that is using G and Z states. However, what happens if we use other non-local states that are not the G and Z? So for 3 qubits, for example, the other family of entangled states is the W states. As we can see, here we have 2 states that are W plus and W minus. They are orthogonal to one another, so it means that we can use them to encode information about the system. And the single qubit holds no information about the system. So once again, information is non-local. However, compared to the G and Z case, if we lose only 1 qubit, the 2 states, W plus and W minus, will be slightly distinguishable. So it means that in this case, using these states to encode information about the system, we expect it to be a little bit easier to reach system objectivity. And this is confirmed by plotting the mutual information, again, between system and environmental fraction. In this case, the non-locality degree is 3. And we are comparing the case in which the information is encoded into the W states, that is this blue line, and the case in which the information is encoded into G and Z states, that is this orange line. As you can see, it's all like the W states always give more system objectivity compared to the G and Z state. So it's always easier if we use W states. At the same time, what we saw for the G and Z is still valid here, in the sense that we still need very large values of redundancy in order to recover state objectivity, even with the W states. So what are the take-home messages from this talk? The first one is that non-locality hinders objectivity. We have seen for 2 different ways to encode the information that whenever we have non-locality, it's more difficult to achieve objective states simply because it's much harder for the observers to extract the relevant information about the system. So even though there's a lot of information encoded into the environment, it's not actually trivial to recover it. And the second take-home message is that redundancy and consensus, they are not the same concepts. So redundancy is how many copies of the information about the system we have into the environment. Consensus, however, is that observers agree among themselves on what are the properties of the system. And so this means that not only the information is encoded redundantly, but also that they can extract it. And in the local scenario, these 2 things are the same. In the local scenario, redundancy and consensus, they're basically the same thing, but this is not true in the non-local scenario. And this take-home message, we can rephrase it in a slightly different way. We can say that in the non-local scenario, SVS does not automatically imply quantum Darwinism. As we said previously, in the local case, it's almost straightforward to prove that if you have an SBS state, it will also have objectivity according to quantum Darwinism. But here we have seen some examples that are not the case. We had states that were perfectly SBS, and yet we didn't have objectivity according to quantum Darwinism. And this was all. Thank you for your attention, and